Okay guys, now let's take a look at the proofs for the first subtopic in chapter 3. I'm going to start the proof by looking at the derivative of simple index function. And if you recall, simple index function is in the form of y is equal to a power of x, where our base can be any number. So that's what I'm going to start with. And next what we are going to do is we are going to apply ln on both sides of the equation, and I'm going to have ln of y is equal to ln of a to the power of x. And by using the rule of log, we know that we can take x to the front, and hence I will then have ln y is equal to x times ln a. And from here now we are going to differentiate both sides. Okay, so then I'm going to have d by dx of ln y is equal to d by dx x ln a. So now I'm applying the concept of finding the derivative. And how do we differentiate the left hand side? Since I have ln y and I need to differentiate that with respect to x, we are going to need to use implicit differentiation. So implicit differentiation says that if you want to differentiate this one, you are going to have 1 over y multiplied by dy by dx. And then for the right hand side, we can differentiate immediately, or you can also use chain rule. Okay, so if you use, sorry, my bad. We are going to use product rule. So if you are going to use product rule, then you need to take note that I'm going to have u as x, and then I'm going to have ln a as b. And from there we can proceed. So u is equal to x and u prime is 1. V is ln a, and if you differentiate ln a with respect to x, you are going to get 0. And putting in the formula of product rule, you are going to get here ln a times 1 is added to x times 0. And we know that x times 0 will be 0. And so we are going to have 1 over y multiplied by dy dx is equal to ln a. And from here, please recall what was our target just now. We want to find dy by dx. So from there, we can just remove 1 over y by multiplying all of those with y. And hence, I'm going to get here is actually equals to dy dx equal to y times ln a. And if you recall my y, I started with y is equal to a to the power of x. And that is what I'm going to put in. And hence my dy dx is actually equals to a power of x multiplied by ln a. And hence we have proven that the derivative for a power of x is actually a power of x multiplied by ln a. Next, we are going to take a look at the proof for the derivative of exponential function. So in this case, I'm going to focus on exponential function in the form of y is equal to e to the power of fx. Here, my exponential function will have another function fx as the power of base e. And here, I'm going to use chain rule when we are going to differentiate this, or we are going to prove the derivative of this function. So what we do first is, please recall, by using chain rule, our formula is dy dx is equal to dy du multiplied by du dx. So I need to have another variable which is u. So I'm going to let u here. I'm going to let u is equal to fx, and hence I can rewrite my y as y is equal to e to the power of u. And from here, I have these two different functions, u and y. So what we can do now is I'm going to find the derivative of both of those with respect to x. So differentiating u with respect to x will give me f prime x, and differentiating y with respect to u, I can't differentiate with respect to x because my function y is in terms of u. So I'm going to differentiate that with respect to u, giving me still e to the power of u multiplied by ln e, which is just 1. So now I have these two terms, and going back to the formula for my chain rule, I now know that I can find dy dx, where dy dx will be equal to dy by du is this one, which is e to the power of u, multiplied by du dx, which is this one, and that is f prime of x. I cannot leave it just like that because we know that if I'm finding dy by dx, then I can't have anything in terms of u. So let's change that back into f of x because we have this here. So you are going to have your dy dx is actually equals to e power of x multiplied by f prime of x, and that is the end of the proof. Thank you.